We're going to solve some more logarithmic equations using properties of logs, but in this instance we're going to find actual decimal approximations to our answers out to 3 decimal places and then check to see that they work. So let's look at this first instance here. We say 6 plus 3 ln x equals 4. I notice that I only have one logarithmic expression here, so the best thing to do is to isolate the log. So that's what we're going to do here, which means we're going to undo our addition first. We say subtract 6 from both sides of this equation. We get this, we say 3 of these ln x things is equal to negative 2. And then we're actually going to divide both sides by a positive 3 here. Cancel those out. We say ln of x is equal to negative 2/3. So here's the important thing here, is that once we've isolated this, we can rewrite it exponentially and kind of solve for what we need here, if that works. And if it doesn't work, we can use the inverse properties of logs. But basically, we say this is base e, it's log base e, so we say e to the negative 2/3 is equal to x. And so we just need to find this here. So we can actually do that. We say e, let's plug this in, e to the power of negative 2 divided by a positive 3 is equal to this here, 0.513-ish. So approximately 0.513, let's write that down. So x is approximately 0.513. And of course we could plug this back in and see that it does indeed work, and you should always check to see that those things do work when you do this. Okay, so I'm going to move on because I know that I want to save some time on this video. So isolating the log here also, we notice that we could divide both sides by 3. We want to get that by itself. So we say log base 4 of 6 times x is equal to 9. Now here's the thing, when we look at this is a little bit different from the last one. It's log base 4. So once I've isolated the log, we can rewrite, I suppose write this over here, rewrite exponentially is what we wanted to do here. Exponentially. Okay, so we say our base here is 4. We say 4 to the 9 is equal to 6 times x. So we can go ahead and divide both sides by 6 here. We can get a purely, real result here. We say it's whatever 4 to the 9th power is divided by 6. That's what our x value is. Now, of course, we wanted to get a decimal here. So we say 4 to the 9th power. We'll do that over here. We say 4 to the power of 9 equals big number, here, divided by 6. So we say 43690. So we have, let's see, approximately 43690 and 2/3. So we'd say 0.667-ish. Okay. And last but not least, this one here. You'll notice that you have 2 logs. I recommend in the last video taking one of these logs and putting it on the other side, because then you'd have a log on both sides with the same basis. You could use 1-to-1 property, but in this case we have this loose 1 over here, so that's not going to help you. What we're going to need to do then is this last resort, which is condense. We want to condense this expression right here. I notice that these have the same basis. They're both common log, so log 10. So I could say, well, the log 10 of this plus the log 10 of this, we could use the fact that if we did that, we get log 10 of the product of these two things. So we get x times x minus 9 is to be equal to 1. Okay, and so here's the deal. We wanted to solve this thing, recall. So if we rewrote this, we got the log by itself, mind you. Rewrite this as the base to the, this power here, 10 to the first, is equal to x times x minus 9 is what we're saying. So, let's go ahead and distribute this. We say 10 equals x squared minus 9x. Let's go ahead and set this equal to 0. So we'd have x squared minus 9x, bring the 10 over here, it becomes negative. So minus 10 equals 0. Does this factor, 2 factors of negative 10 that have to be a negative 9? And yes, it does. We say x minus 10, x plus 1 equals 0. So we get 2 zeros here. We get negative 1, we get 10. And the important thing to point out here is this. You should check them both. And so here's the thing. I will actually check it on this one. If you plug this one back in, log base 10 of negative 1 plus log base 10, I'm just plugging this back in the original expression, negative 1 plus, minus 9. Minus 9 equals 1. The thing is, you get log base 10 of negative 1, which in and of itself is an absurd statement, because you're saying 10 to what power equals negative 1. There is no answer to this, so this doesn't exist. This one here, we say log base 10 of negative 10. That's obviously not going to exist. Same reasoning. We say 10 to the power of what equals negative 10. That doesn't happen. So we'd say that only one solution exists here, and that'd be our 10. Okay, when you plug it back in and check to see that it works.